Thank you. Yes, and I'm grateful for this invitation, which probably breaks more rules than probably every rule. It's based on joint work with Menachem and Magidor, and recently with a long list of people, most of them here, something I refer to as square. It's a two-part lecture. The other part was supposed to be given by Menachem Magidor, but he's indisposed. So Ralph kindly stepped in. So in the afternoon, Ralph will give a more model theoretic account of some of the things that I'm talking about. So the topic of this talk is this inner model CL star, which has this L star, which is just an abstract logic, or in fact more this talk, concrete logic, which extends first-order logic. There are many such logics. They were studied a lot in the 70s, 80s, and not so much later. But some of them have absolute, even finite syntax, like high-order logics and logics with generalized quantifiers. This will be relevant in this talk. But some of them have non-absolute syntax, but have absolute semantics, like infinite logic L infinity omega, or the game logic L infinity T. And then there are some which have neither. Okay. Now, since I'm talking about inner models and introducing a new inner model, several questions arise. For example, is it really new? And in many cases, it's not new. But suppose it is a new inner model, then we should evaluate or contemplate what would make an inner model interesting or relevant. And these kind of questions come up, and we try to also establish for our sort of the favorite examples some of these. So forcing absoluteness of the theory, is supporting large cardinals, rising somehow naturally. I mean, logic is so general concept that one can invent an ad hoc logic for almost anything, and then it is not so interesting. And they should decide, preferably questions like CH, because that would sort of indicate that we understand the inner model somehow. And we are mostly so far focusing on inner models that satisfy axiom of choice, something which became more an issue after we had started escape here. Cape, yes. Thanks to some observation of Cape. Okay. Okay, so as I said, sometimes we hit the old inner models, like first the logic is L omega 1 omega is L omega 1 omega is L of R, L omega 1, you get the Chang model, which was introduced in 1971 in the same proceedings of Symposium of Pure Mathematics. Myhill and Scott had a paper in which they showed that secondary logic gives Hort. So here some well-established logics give rise to well-established inner models. So these are not new. As it turns out, as I learned recently, Klaus Glöde in 1978 in Tübingen, and actually had the same approach as us. Difficult to invent something new. There's always someone who invents before, it seems. Anyway, so he considered the case that the logic is CFC absolute. Its syntax and semantics are absolute in transitive models of CFC. And then he showed that you get just L. But he considered absolute fragments of infinitary logics. He did not go anywhere. He did not go beyond infinitary logics. But Of course, the Q alpha, there exist at least Aleph alpha elements, satisfying a formula, which is the original example of Mostowski, 1957, when he introduced generalized quantifiers. That is absolute if you have Aleph alpha as a parameter, so you also get just L. So the original generalized quantifiers don't give anything. Then later, I think in the 70s, Magidor and Malitz introduced this higher dimensional quantifier, which quantifies over n tuples and says that in a formula with n free variables, this is true if there is a set X, at least of size Aleph alpha, so that this capital X is in a sense homogeneous. So any n tuple from there satisfies the formula. And well, this for Aleph 0, this is absolute, so you get nothing new. But for Aleph 1, you can express through Trinity, so it is not absolute. But consistently, you can, by using selective filling of subsymmetries over L, then you can show that this is not L. But somewhat surprisingly, if 0 sub exists, then this collapses to L. And it's based on this consequence of Robotham property that if you have indiscernibles for L and you have a set in L, and there is an uncountable set B in V, such that the square of it is contained in this constructible set A, then there is such a set in B. You sort of homogenize the set with Robotham's theorem. And this gives rise now to this concept that logic, as I said, logic is a very general concept. You can think of anything and make it a logic. So being a logic is nothing more than being closed-under isomorphisms. But let's say that the logic is L-tame if the inner model generated by it is L. Now, as a the kind of logician that I am, I ask the kind of question is that can we characterize L-tame logics, and does L-tameness have model theoretic consequences? Potentially like Leeuwenhuis-Golem, compactness, interpolation, number this, Leeuwenheim number that. But I don't know actually any, so it is a mild question. But it arises, I think, naturally. So now after this little introduction, I will actually define this CL star. So CL star is defined by simultaneous induction. We define this truth definition, and the hierarchy is generated by it. So the truth definition is just the pairs alpha phi alpha, so that J prime alpha with the previous levels satisfies phi, and then the J prime alpha hierarchy is the usual Jensen hierarchy with this full predicate there, extra. Okay, so on the other hand, there is what I call old definition or original definition, which is like the Gödel definition of L, where we take the definable subsets, and then instead of first order definable subsets, we take L star definable subsets of the colored level. And they usually agree, and I have some arguments why, but as Gabe Goldberg observed, it's not clear that we get axial choice with this definition always. Okay, so whatever the logic is, these two classes are transitive models of CF and containing all the ordinals. And if this syntax is KB absolute, then the new definition also satisfies axial choice by general properties of the J hierarchy. And now this condition which is needed for it seems, for the axiom of choice. So usually axiom of choice for L is defined so that by using definable global well ordering, which is based on truth definition of first order logic in first order logic. And it's kind of long, but unproblematic for first order logic. For other logics, it may be problematic, but here is the concept. We say that the logic is adequate truth in itself if it can define its own truth in itself. So we have this kind of equivalence. So this formula SAT for satisfaction is in the logic itself, so that this holds. And I mean, there is this thing that from some perspective, logic cannot define its own truth, but in this sense, most logics can define its own truth, like first order logic, for example, can define. But for some logics, there are some difficulties, and we don't know how to overcome those difficulties. But for example, if we add all these Q0, Q1, and so forth, infinitely many, of course, this cannot be adequate to truth in itself, because how can one sentence in this logic define the truth of all those quantifiers, because one sentence contains only finitely many such quantifiers. So it's not always true, and sometimes not for trivial reasons. So if the logic is adequate to truth, then we can do what is done in Gödel's proof of axiom of choice. We can define a global well ordering, and and then we get also for this original minimal C O L star axiom of choice, and very little is known about the difference between in these two versions of the inner model. It's kind of open question. There is this example, which is admittedly ad hoc. It just did this for the purpose of getting the result. So this QSTN quantifier says that formula psi is interpreted as an order type of Aleph n plus 1, and this other formula defines the stationary set of points of cofinality Aleph n. Now, if we add to first order logic all these quantifiers, then axiom of choice may consistently fail. There is this is in a sense trivial like this, but this is truly trivial because you can simply use Lerner's column arguments to show that it's not adequate to truth in itself. While here everything is a bit more complicated, and we need it for C. So here is an example where C0 L star is different from C L star. And however simple this definition looks, it turns out that we cannot really separate it from the original definition. So let's go back to this inner model. When we consider different logics, and there are many, I don't want to go into how many different logics there are, but usually we define the sublogic relation like this. L star is a sublogic of L plus if, okay, so every model class which is definable here is definable here. Intuitively, if the formulas of L star are also formulas of L plus and have the same meaning. But we can define a different order. L star is less than prime L plus if the inner model is a subset. Inner model of L star is a subset of the inner model of L plus. So this gives a different aspect of kind of a different invariant of a logic. We can gather kind of different kind of information about logic by looking at this order. Let's take an example, the Hertig quantifier, which says that two formulas are satisfied by equally many elements. This is old and kind of natural, a priori natural. And it seems quite strong. For example, if you look at its delta extension, then it can be the same. It is the same as a delta extension of second-order logic in V equals L, and even if you are in an extended model without a Woodin inner model for a Woodin cardinal. But on the other hand, the inner model is relatively weak, as was shown by Philip Welch. The Kukri, which is a sub for an inner model with proper class of measurable cardinals, is not there. So this means that this is rather weak. Although the logic seems strong, but only in inner models, but even in quite strong inner models. So we get a set theoretic perspective of the strength of logics. In fact, this inner model from the Hertig quantifier hits the extender model hierarchy quite well. So it is you take the inner model for proper class of Woodin cardinals, for proper class of measurable cardinals, and iterate it and take a Prickly type extension, and that is exactly the CI. So it is, in that sense, it's not a new inner model. But if we take the inner model of second-order logic, we get exactly Hod. But the inner model of any logic with finite syntax is a sublogic of is definable in Hod. So that means that second-order logic is maximal in this hierarchy of logics, which fits the intuition among logicians that second-order logic is extremely strong, too strong for any reasonable purpose. But here is a technical result of its strength. It is actually maximal. So you take third order, fourth order, whatever type theory, they are all sublogics of this. In this, with respect to the inner model. There's a related inner model, Hod 1. If you only take the sigma 1, 1, the existential second order part, existential part of existential second order logic. And this is surprisingly strong. Well, it has a Magidor Malitz and it has a Hertig quantifier. But it turns out that this is exactly the same as the inner model defined by the Henkin quantifier. This is Henkin quantifier. It says that for every x and every u, there's a y depending only on x, and there's a v depending only on u, so that's fine. Introduced by Henkin in 1961, or in fact 1959, I think, already. So it's a very old. But we get equality here. Now there's a consistency result that Hod 1 can be different from Hod. We start with infinitely many weakly compact cardinals in L, and we get a forcing extension by selectively killing some weakly compact cardinals and then resurrecting them back, and we get the kind of sandwich effect. That this set is not in Hod 1, but of course it is in Hod. So this is an example where the delta extension of a logic gives gives rise to a different model than the logic itself. Let's go back to what the delta extension of logic is, because it may not be familiar to you, but it is the same as, it is analogous to delta 1, 1 extension of a point class. But it is, you take model classes which are projections of definable model classes in a bigger language, bigger vocabulary, but also their complement is a projection of a definable model class. So they are projections and their complement is projection. So this is what delta is. And it preserves model theoretic properties. It preserves axiomatizability, compactness, Levenheim's column, theorems, Levenheim's numbers, and so forth. So it is considered in model theoretic terms, it is considered a mild extension, but it doesn't preserve the inner model. Okay, now the first no, it's not the first, but anyway, the cofinality quantifier. So this was introduced by Sala. It says that the binary predicate, definable predicate, is a linear order of cofinality omega. It's remarkable because it is axiomatizable easily. I mean, intuitively axiomatizable and can be proved. Fully compact and has down a Lerner-Skolem theorem down to Aleph1. So we denote, for some reason, the inner model by C star. A simple observation, which is the basis of a long development of results, is that if zero sub exists, then it is in C star. And more generally, C star is closed under sharps. I give the proof because it is the basis of more and more elaborate results. If we take the set of ordinals below something, which are regular in L, but they have cofinality, uncountable cofinality. Of course, this is in C star. But it can be proved with an argument which is not very difficult, that it consists of L indiscernibles. Hence, we can define zero sub. Now, Philip proved a stronger result that the O-Kukri is in C star. And more is known today, and I think Ralph will probably talk about what more is known about what kind of subs are in C star. But it is not known whether there is a measurable cardinal in C star. That's about C star, that's like the most notoriously open question. We know that if V equals C star, then there is no measurable cardinal by the Scott theorem, the first result about ultrapowers, models of set theory, and by result of Kuhnen, if E is an infinite set of measurable cardinals in V, then E is not in C star. This is like the Kuhnen's proof that axiom of choice fails if there are uncountably many measurable cardinals. It fails in the Chang model. But here we have axiom of choice. So we turn the table and we prove that that set cannot exist. If there's an inner model for a measurable cardinal, then there's one in C star. If there's a Woodin cardinal, then omega 1 of V is strongly Mahlon in C star. This uses stationary tower forcing countable stationary tower. But we don't know whether this omega 1 is weakly compact. But everything above omega 1, if there's a Woodin cardinal, then everything above that and below the Woodin cardinal is weakly compact in C star. Also uses stationary tower modification. And if there's a proper class of Woodin cardinals, then the regular cardinals above Aleph2 are indiscernible. Of course, Aleph1 is special because it has a property that every ordinal has, limit ordinal has cofinality omega, but above that, they are indiscernible. And then there's a computation in L on mu that C star is the omega squared iterate plus the Prickly sequence, and it has been generalized to longer sequences of measures. The theory is preserved by forcing if there's a proper class of Woodin cardinals. Then about continuum hypothesis, which is another open question. We know that there are at most Aleph2 of V reals in C star, but Aleph2 of V is weakly compact in the presence of large cardinals, so it's not so interesting. But with some large cardinals, we can find a cone of reals such that C star of X satisfies the continuum hypothesis by using the Martin determinacy. And it is consistent relative to the consistency of indexes for cardinal that V equals C star and continuum is Rf2. Of course, it can be also Rf1 if V equals L. But we don't know whether large cardinals imply that C star satisfies CH. So this is also seems like a little bit difficult. Has been open ever since the beginning. So now another example which has been studied extensively is stationary logic. This is a different kind of logic. This is not a generalized quantifier in the sense of Andrzej Mostowski. This was introduced in one form by Sela and then by Kaufman, Mackay, and Barwais in a kind of second order form. So we talk about countable subsets of the universe M, and we stipulate that there's a club of countable subsets which all satisfy this phi. So we're not saying that there is some countable subset which satisfies phi. We say that there are many, many, many countable subsets. But we are not saying all countable subsets, because those two would lead to a different logic. We say that there's a club, that's a kind of a balance. Measure one set of countable subsets. And you can express Q1 and the cofinality logic there, but we don't know whether this is adequate to truth in itself. So this is what Gabe Goldberg pointed to us, that we claim to the, because it is not obvious, so we don't know what it is. And we don't know whether in the original version the AA model satisfies axiom of choice. This capital A. No, it's a countable subset of M. It is a predicate here. Yeah. Yes. Sorry. Yeah. I put there M with the predicate A. Between L of what this is. Oh, sorry. Yeah, this should be like this curly L.
Oh, this should be the curly L. Okay.
And this is, yeah, okay, yeah. So it is like first logic where you add this. Now what was just said that this is a predicate in M. It is very important, very surprising that I always forgot to put it there. But anyway, that's the truth. So from a set theoretic point of view, we look at subsets of M which are in V. Very important. Okay. Now, this an important property that then emerged and was isolated is what we call club determinacy. So the levels of the AA model satisfy this kind of dichotomy that either for any definable subset, either it contains a club or its complement contains a club. So all definable subsets. For the definable subsets, it is like a club filter is like ultra filter. And a major part of the understanding of the AA model is a proof that club determinacy follows from a proper class of Woodin cardinals, which is based on a stationary tower, and we need a proper class of Woodin cardinals because we do some preparatory forcing, and then we need Woodin cardinals after that. We take a stationary tower forcing, and then we show that in the inner model that comes from the stationary tower, the AA model is actually the same as a modified AA model in V, modified so that we consider only subsets of size, no, we consider subsets of size less than delta rather than countable. So countable becomes less than delta. And this is in V. And this is not in V because it's a generic. So this generic object is actually the same as this object in V. And it uses this kind of technical lemma that if you have a lambda, which is Woodin, and G is a countable generic, countable stationary tau forcing generic, and you have a subset of lambda which is stationary in V, then S is stationary in VG, which is not trivial, non-trivial proof. We can also derive club determinacy from PFA with a kind of soft argument. There's a proof, I think here, that from proper forcing axiom it follows that for any set there's a model with a proper class of Woodin cardinals which contains that set, and then we can go back to this. Okay, so now because we have these club filters which are ultrafilters relative to definable sets, we get that all regular cardinals above F1 are measurable. So we get a proper class of measurable cardinals in this. With this C star, which is a submodel of this, we don't know if there's a single measurable cardinal, but here we have a proper class, and it's also forcing absolute. So now I go to the concept, what we call AA primus, which we use to prove continuum hypothesis, and hopefully it can be used, and I know it can be used to prove something else also, but it is much less developed than the primus that John talked about, and in fact, I wouldn't be surprised if some people in the audience were upset that we call these things primus. But we call them AA primus. Okay, so an AA primus is a structure like this. So there are these two predicates. This is like the truth predicate for lower levels of the hierarchy, and this is like a truth predicate for the level J alpha. And then here is a continuous sequence of unary predicates. So here we build a club on the final model when we iterate this omega 1 times. These sequences grow into a club. And that club is used to show that this truth predicate here, or this fake truth predicate, is actually real truth predicate. And then we pull with us this fake truth. So the fake truth here, by fake truth I mean that these are just theories. They are just claims. There is no substance. It's just the claims. You can claim anything. They claim things about the club filter, but we make sure that it is somewhat credible, the claims, and that they accumulate when we iterate into real truth. But we have to resort to this trick of just talking about theories rather than real filters, because after all, most of the time we work with a countable primus, and in a countable domain, the AA quantifier is really, there's nothing, because yes, so this is really meaningful only in uncountable models. So there are, for this kind of structure to be called an AA primus, is it so that I have time till 5 past or 5 past? Okay. sorry, he sat there. So it's okay, so there are 9 conditions for this. I won't go through them. I just said intuitively that these are theories in the AA logic, and they have to be somehow coherent with some kind of elementary truth. And technically, when you formulate it, then it is kind of, you have to be careful so that it's preserved by ultra powers and so forth. A canonical example is, as I say, the real truth on the levels, earlier levels, and the real truth on this level. That's a canonical example of this, what I call fake truth, that is not fake at all. Now, to compare these premise, we define this concept of weak elementary embedding, which means that it's elementary embedding when you leave out the actual truth, the truth of the level itself. You only have this predicate which talks about the previous levels. But for the truth of the level, we have this condition that for any AA. Oh, sorry. In this case, we only consider first order element truth, preservation of first order truth. But for this truth predicate, the star here, we allow or we demand that for any ASE formula, parameter satisfied in this star if and only if the image satisfies in this. So we have to preserve the AA truth in the sense of these theories for the part of the star, but otherwise we have to be coherent in the sense of first order logic. Okay, now let's see how to define the iteration. For iteration, we define an ultra power, and we cannot take as ultra power the usual ultra power because we don't have any ultra filters. So we define an equivalence relation between formulas if and only if for most predicates S, okay, so this is here is the first element satisfying this formula. It is defined here. F phi denotes this canonical well order of the J hierarchy. Minimal X satisfying this formula. Okay. If for most S, the minimal is for phi is the same as the minimal for phi prime. If this statement is in this T star, which is our theory of the real truth, but it's so far only partial theory. And the ultra power we form from the equivalence classes, we embed every element with a kind of canonical embedding. And for predicates, we define a predicate is satisfied by equivalence classes if for most values of S, the first element sequence is satisfied in the sense of T star. Okay, and then we have in this pre-mouse, we have this sequence of unary predicates, which are approximations to a final club. So we have to, when we iterate, we have to extend always, we add a new predicate P star, which is just the image of the previous model. The previous model becomes a new predicate in the sequence in the ultra power. So when we take the ultra power, we add the previous, the ground model universe as a predicate. And this, if we can preserve well-foundedness, then this will preserve the pre-mouse axiom, AA pre-mouse axioms. And here is a, I won't go into details, but this is a standard way to make sure that the ultra power is well-founded, and we get an iteration, and we say that the original pre-mouse is iterable, mouse if all these iterates are well-founded. And now here is the main thing about this is that when we take the omega 1th iterate, then formula of stationary logic is true, really true, if and only if this story, T star, this fake story says that it is true. So by building this club, we make sure that the stories become real truths. And so this is typical in, well, for example, in ordinary model theory, classical model theory, that you have a model which is not quite what you want, and then you iterate by taking a elementary chain, and it is more like what you want. So then, if club determinacy holds, because we use that in the proof all the time, then continuum hypothesis holds. And the proof of this is like Silver's proof of GCH in L of mu. But it's based, of course, on this notion of mouse. And we get the delta 1,3 well ordering of the reals here by looking at the mice. And of course, you can compare mice. Well, as we do it, if you have two pre-mice, AA mice, you can iterate, and if you iterate omega 1 times, then they hit the real hierarchy of the AA model, and then whoever comes first is smaller than the other one. So you can compare these. Okay, there is an interesting recent, more recent version AA plus, in which when we take this predicate A and add it here, now I'm more careful, and you take the next admissible set, then only then we insist that phi is true. So we don't consider truth in the model that we start with, but we consider in the next admissible set, and we allow this countable set. We take countable set from V, and then we take next admissible set. So the advantage of this is that if you have a well-founded extensional structure in AA plus model, then its transitive collapse is there also, which is not clear that if it is true. Then Otto, who is here, has worked out the details of AA plus and proved all the results that I mentioned about AA model also hold for AA plus. And when we consider mice, real mice, in the sense of real inner model theory, which are like zero sword or such, then this becomes relevant. It is there's a clear difference between these two in how you construct mice inside, because these constructions use a collapse. I will skip this, and I just say that there is a third kind of model, which is where you take the secondary logic over countable subsets. You don't ask, is there a club of countable subsets? You ask if there is even just one. And surprisingly, at least to me, this is very much like C star and the AA model, but not either of them. Some recent developments, because my time, I think, is approaching, and this night. Yeah. Okay. Assuming a proper class of Woodin as a reals of AA model and also C star are in M1, and the AA model has no inner model with the Woodin cardinal. So there is a bound on. Of course, since we have sigma 1,3 well ordering of the reals, then and the AA model also is closed under sharp, so there cannot be an inner model with the Woodin cardinal. So this is an absolute bound on what we can get inside these models. Assuming club determinacy again then ultra-power axiom of Goldberg is true, and GCH can be proved here. Assuming club determinacy again, if kappa is a regular cardinal in a model, and its cofinality in V, this should be V, is greater than or equal to omega 2 of V, then it is a higher measurable cardinal in this sense. Moreover, for the omega 3 of V has Mitchell order at least 3. So we get more than a proper class of measurable cardinals. If V equals L of mu, then we can prove that V equals the AA model. And there's an ongoing investigation on what kind of real mice can be found inside these models. It seems like an interesting question. Thank you.